All right, today, folks, we are dealing with Gauss's law, and I can tell you that if you're taking the AP Physics C Electricity and Magnetism exam, 70% of exams since 1979 have included a Gauss's law problem. The other 30% have always been some kind of electrostatics, electric fields, or electric potential problem. 30% of the E&M exam is electrostatics. So a very, very high probability that this is going to be on the exam. So we definitely want to focus, pay attention, and ask questions if you don't understand. The good news is that this is actually easier than what we just did with electrostatics and Coulomb's law. In fact, the entire purpose of doing this is to make it easier than Coulomb's law. So although it can be challenging because it's something we've never seen before, the whole purpose is to make it easier. So if it's not easier than Coulomb's, you may be doing something wrong. So let's start off with the concept of what we call electric flux. Now, to talk about this, I'm going to use really a good analogy for this is when you have a fluid flowing, we have what is called volume flux. So I'm just going to delve into the analogy of this. Before I even talk about electric flux, I'm going to talk about volume flux for fluid flow. And if you end up, for some reason, taking the AP Physics 2 exam, and a couple of you are interested in possibly taking that next year, this is something you would have to know. Volume flux is this. If you have a tube of water, here is a tube of water. So it's water in here. And we've got water flowing this way at speed v. And this area right here, the cross-sectional area of the tube is A. Then volume flux is simply equal to A times V. Now let's figure out what the heck that really means. What are the units of A times V? Units, in this case, what are the units of area? Meters squared, and usually we do like these brackets when we're talking about units. Meters squared, what are the units of speed V? Meters per second. So notice that this gives us the units cubic meters per second. And that makes sense because volume flux is just the rate of flow of a fluid, and it's in cubic meters per second. So if I get, it's similar to gallons per second, that's always also a unit of volume flux, but if I have 10 cubic meters per second of water coming out of the end, that is the volume flux. How much volume is issuing out of the end of this, let's say, per second. So it's pretty easy to do it that way. Now, it's a little bit trickier, is this. What if, and we often talk about like how much volume flux is going through a surface, which may be an open surface or it may be a closed surface. Let me talk about how would we have to adjust this in the situation where that's how much A times V is how much water is coming out of that end like that. But what if I asked kind of a similar question and I had the similar situation right here, pretty much exactly the same. I've got the water moving at speed v, and I've got also a screen of area A, but what if the screen was not like this? In fact, what if the screen was like this? Exactly parallel to the water velocity. How much water would actually go through that screen? Hint, here's the path of the water. How much water goes through that screen of area A? No water is going through that screen. So we can see that it has more to do with the velocity and the area of this thing. We are going to need to somehow indicate an angle. And here's how we indicate angles. What we do is for this area A, we represent this area A with an area vector. The area vector is perpendicular to the area that we're talking about, this is the area vector A. It's got magnitude of A, whatever the area is, but it's pointed perpendicular to the surface. So that's important because when you figure out the angles, it's not the angle between the actual surface and the what we're going to be talking about later as electric field, or in this case, velocity. It's not the angle between the velocity and the surface. It's the angle between the velocity and the surface vector. And this is our surface vector right here, representing the area A. And it's kind of a good way to do that because with one vector, I can represent that whole area. It's perpendicular to the surface. So check this out. We're getting the volume flux. In this example, the flux equals 0 for this example here. So here's our area vector A. That's our A vector representing this. Here's V. What is the angle when I get a flux of 0 between V and A? It's 90 degrees. So what trigonometric ratio is probably going to be involved here when you get, for 90 degrees, you get 0? So that's going to be a cosine. So are we talking choice 1, a dot product, choice 2, a cross product? That's going to be important. Choice 1 dot, choice 2 cross, which is going to be the type of product we're going to be dealing with. If you say choice 1, a dot product, you are right. And let's go ahead and give an example of this. To figure out the flux when you have a situation like this, again, we've got our exact same tube of water, and we've got still the same velocity v right here. But this time, here is our piece of screen that we're going through. So in this situation, we've got our A vector pointing this way. Now you may say, how do you know which way the A vector points? Does it point, down to the right or up and to the left? When you have, really it's only easily determined when you have a closed surface. The A vector always points outside of a closed surface. What is a closed surface? It's any surface that's got an inside and an outside. For example, a box or a sphere, those are closed surfaces, and in all those cases, the A vector always points to the outside. For an open surface like this plate right here, you get to decide which way you want the A vector to point. But in this case, notice that I've got, in fact, what I'm going to do is I get to decide, so I'm going to decide to do it like this, the other way. I'm going to make my A vector pointing, it's behind there, right there, and it's pointing that way. So it is perpendicular to this surface A, so we get to decide that way. And the reason I wanted to put it that way, because when you want to figure out angles between two vectors, do you put them head to tail to tail, or something else? You don't put them head to tail when you're figuring out the angle between two vectors. You put them tail to tail. Notice if I want to figure out the angle between this finger and this finger, you put them tail to tail. You don't put them head to tail. That's not going to give us the angle between them. Tail to tail is always how you figure out the angle between. So this is going to be easier for me to put them tail to tail. That's why I did it that way. I'm going to pick up this velocity vector, move it over here. There we go. There's my velocity vector. And that right there is what I'm going to call my angle theta. The angle right there will indicate that as theta right there. So when you figure out what the flux through here is, how much basically it's how much water's getting through that little screen that I've created there. The flux here, in this case it's for water, is equal to not just A times V, but it's V dotted on the A vector. And notice it's a different angle between the A vector is at a different angle than the actual area itself. It's always the A vector. So that means just VA times the cosine of the angle between those two vectors. You always put them tail to tail to figure that out. So, and does that make sense? Does that work for this situation right here. What's the angle between my V and A for this situation up here? It's 90, so how much flux, how much flow per second is going through that screen? Zero. For this one, it's something that is greater than 0, but it's less than 90. So let's say it was 45. I'd be getting about half of the amount that's coming, that would be coming through a tube this size. If that's the area, similar area, I'd be getting about half of it because we're missing some there. And if you had it perfectly like this, if your area was in fact the end of this, what is the angle between, I'll draw my A vector right here. Let me get rid of these things. What is the angle between my A vector? I'm not even going to draw it on here. What is the angle between the A vector and the velocity? It's tricky. Yeah, it's 0. Here's my A vector right there. That's the A vector representing that end area there. And notice I would get the full-on V dot, it's a dot product A, which is equal to VA cosine of, what's the angle between them? 0. That is equal to 1. So I would just get V times A. Get the full volume flux there. Cool. That is volume flux. Let's now talk about electric flux. This is just an analogy for what we really want to talk about, electric flux.